Let me take a deep breath. Hello everyone, I'm Jiacai from Nanjing University. I'm a second-year PhD student advised by Yue Li, who co-runs the Pascal research group with Tian. Today, I'll try my best to present this work on behalf of the first author, Qinlin Chen, who was unable to attend due to visa issues. Our paper is titled Exploiting Sophisticated Static Analysis for Verilog, the Prominent Hardware Description Language. In this talk, I'll first discuss the untapped potential of hardware static analysis, and then I will introduce Qi, the first general-purpose static analysis framework for Verilog. After that, I will show what hardware static analysis looks like in practice. Finally, I will present our preliminary experimental results on applying hardware static analysis to diverse application domains. Let's start by talking about why we want to do static analysis for hardware. If we look back at how static analysis has evolved in the software world, we can observe a large amount of untapped potential of static analysis in the hardware world. In many ways, hardware development resembles software development. Hardware is programmed in languages like Verilog, and its quality is ensured through techniques such as simulation-based testing and formal verification. I cannot find my curses. I have found. Oh, it's on the other screen. Okay. Oh, I found it. Sorry. However, as of 2026, static analysis in hardware is still underutilized. The overwhelmingly dominant hardware static analyzers are linters. They provide basic syntactic checks, such as naming conventions, style rules, and simple pattern matching. This is similar to software in the early 2000s. At that time, standalone software static analyzers largely meant linters as well. However, over time, as software became more complex and more diverse, static analysis has evolved significantly. Thousands of analyses emerged for bug detection, security assessment, and program understanding. These are sophisticated semantic analyses beyond linting that reason about program logic, properties, and intention. They have led to widely used tools like clown static analyzer, covariety, p-tend, and many other tools. Now, if we turn back to hardware, we are seeing a similar inflection point. Hardware designs are also becoming more complex and more diverse. We are seeing many domain-specific hardware accelerators emerging for areas like AI, graphics, bioinformatics, and so on. We believe static analysis in the hardware world could likewise evolve into sophisticated semantic analyses that help detect hardware bugs, improve hardware security, and deepen our understanding of hardware designs. And today, this area is still underexplored. Therefore, to support the exploration and exploitation of hardware static analysis, we developed Qi, the first general-purpose static analysis framework for Verilog. Qi was a challenging effort. We spent 4 years developing it from scratch, drawing on our sustained communication with industrial hardware practitioners, with an in-depth understanding of formal Verilog semantics, and our decade-long experience in fundamental static analysis research. Now it has grown to over 100,000 lines of open source code, and I'll introduce it for you. This is an overview of Qi. It summarizes its main components: the front end, the IR intermediate representation, the analysis manager, the general purpose fundamental analysis, and the application specific analysis. Although Qi is a static analysis framework, our goal is to enable real-world adoption of sophisticated hardware static analysis beyond the linting. Therefore, Qi comes with a set of out-of-the-box built-in application clients as demos of its capabilities. These analyses are motivated by the needs we gathered from both hardware literature and our communication with industrial practitioners. And they span diverse areas as mentioned before. As a framework, Qi's most important component is its fundamental analysis. These analyses are designed to be reusable building blocks for diverse application-specific analyses. On average, each fundamental analysis is already reused by about 10 built-in application-specific analyses in Qi. These fundamental analyses address essential hardware characteristics that handle Verilog's 4-valued bit vector semantics, capture how synchronization and concurrency work in Verilog. They also support analyzing complex hardware control and data flows. The remaining part of Qi is its infrastructure. We provide an analysis-oriented front-end and IR for Verilog. It also supports analysis of incomplete hardware programs because in hardware practice, encrypted IP cores are common and their Verilog code is typically not available. In addition, we provide a user-friendly analysis manager that simplifies analysis development. We hope our framework can make life easier for both Verilog analysis users and future Verilog analysis developers. If you are interested in developing analysis for Verilog for hardware, you may wonder these questions about hardware analysis problems, insights, and challenges. To concretely answer them within a short time frame, I'll use a motivated example, missing reset analysis. It has a closed software analog used before initialization, or UBI. In both cases, an undefined value can propagate throughout the program and cause serious consequences. Since you may not be familiar with Verilog, I'll briefly give some background. Let's start with how Verilog code models hardware registers. Registers are a common hardware concept. They store values that represent the current circuit state and update on clock age. Here's a simple example of a register that accumulates input values on each clock age. The first line declares a register ACK, which is an accumulator. Line 2 declares 2 wires in, which carries the external input values, and the clock signal that toggles between 0 and 1. Lines 3 and 4 specify an always block, which says whenever the clock transitions from 0 to 1, which is called a positive age, as specified by this POSH keyword, ACK is updated to its current value plus the input value in the current cycle. However, when a circuit powers up, registers start in an undefined state. To address these, hardware designers typically include a reset signal that users can assert to trigger the reset logic, forcing registers into a predefined non-state. In this example, a new input wire reset is added in line 3. Inside the always block, a reset case is also added. If reset is asserted, ACK is set to 0 as its initial state. Otherwise, accumulation update is performed as before. The table on the right shows how the value of ACK changes over time. The first column shows clock cycles. Each line corresponds to a clock cycle where clock toggles between 0 and 1. The second column shows how the input value changes at each clock cycle. In cycle 0, ACK is undefined because the circuit has just powered up. Then line 5 is executed as triggered by this positive clock age. Since reset is 1 in this cycle, line 6 executes and sets ACK to 0 for cycle 1, not for cycle 0, for cycle 1. This is a special semantic of this left arrow assigning operator, which is called non-blocking assignment in Verilog. In cycle 1, reset is 0, so line 8 executes. Because in S2, ACK will take the value 2 in the next cycle. 2 plus 0 gives us 2. Similarly, in cycle 2, we can compute that ACK becomes 5 in cycle 3 in a similar way. With this background, we define the missing reset problem. A register has the missing reset problem if its undefined value is used infinitely often after reset. The key here is infinitely often. In contrast, undefined values being used only finitely often is typically acceptable because in hardware, unlike in software, defined values can take time to propagate through the circuit, especially in pipeline designs. Here is a simplified pipeline that propagates values from register X to Y and then to Z. During its execution, we can see that after reset, X becomes 1, and its value is propagated to Y and Z cycle by cycle. So these registers are eventually defined, which is good. Here is an example of the infinitely often case. Even though X is reset to 1 initially, in subsequent cycles, the undefined values in Y propagates to X and then feeds back to Y. This happens repeatedly, so the undefined value keeps circulating infinitely, which is a bad case. The missing reset problem may look similar to the UBI problem in software. However, they are fundamentally different. UBI flags a variable if its undefined value is used once in any possible software execution. However, in contrast, the missing reset occurs when a register's undefined value is infinitely often used after reset. Therefore, addressing missing reset requires hardware-specific insights rather than directly reusing approaches designed for UBI. To solve this problem with static analysis, our key insight is that only non-reset registers involved in circular dependencies can have missing reset problems. Here is the previous problematic example. This is its hardware dependency graph, which encodes all the dependencies in the design, like synchronization, reset, data, and control. From the graph, we can see that X and Y form a circular data control dependency. However, register Y is not reset, so it has the missing reset problem according to our insight. For the sake of time, I will leave Sauna's argument of this example analysis to the paper. After getting at least a sense of the missing reset problem and analysis, we can now talk about the challenges. What challenges arise in building a missing reset analysis? First, we need to understand how Verilog variables map to physical registers, clocks, and resets, since the problem is defined on top of these concepts. Traditionally, this information is not available until after the lengthy hardware synthesis process. Invoking a synthesizer to obtain it can take over an hour for a million-line design. In contrast, Qi provides analysis that approximates this post-synthesis information in just 3 seconds with high precision and recall. In addition, we need hardware data flow and control flow analysis to construct the graph structures we need for the missing reset analysis. To understand how variables are mapped to registers and clocks, we also need analysis for capturing Verilog synchronization characteristics. To enable more precise intermodal reasoning, we also need module hierarchy analysis and other supporting analyses. In summary, building a sophisticated Verilog analysis beyond the linting does require a substantial foundation, which is exactly why we provide Qi. Qi provides all of these supporting analyses and even more to be reused across a wide range of clients. This is a whole picture of Qi's analysis suite. Missing reset is just one small bug detection client among them. The nodes on the left are the fundamental analyses, and the nodes on the right are application-specific analyses. The edges indicate analysis dependency relations. We omit the edges between fundamental and application-specific analysis because the diagram would otherwise look cluttered. As mentioned before, each fundamental analysis is reused by about 10 application-specific analyses, which is why we call them general purpose. We call them fundamental. Finally, let's look at some preliminary experimental results of Qi's application-specific analysis. On hardware bug detection, unlike software, hardware tends to contain fewer but harder to detect bugs. That's because hardware designs typically undergo extensive simulation and rigorous verification, as hardware defects are too expensive to fix if escaped into production. Unlike software, you can deliver a patch over the internet. You cannot deliver a hardware over the internet. Even so, our analysis detected 18 bugs in 8 categories across hardware projects averaging 1.5 thousand GitHub stars. Half of these bugs were previously unknown, and all of them have been confirmed by the developers. Moreover, all of these bugs are beyond the capabilities of existing linting tools. On hardware security analysis, our Verilog taint analysis can find 15 information leaks from the well-known Trust Hub benchmark. Qi can also detect a class of hardware Trojan that exploit Verilog's special X-value semantics to hide their malicious behavior. On hardware program understanding, we evaluate Qi on 3 representative tasks, inferring clock signals, reset signals, and registers, and achieve 97% precision and recall on average. On hardware code optimization, we can identify a lot of useless signals that can be safely removed. Overall, these preliminary results demonstrate strong potential of hardware static analysis. With Qi's underlying framework support, the implementation effort of this application-specific analysis is also modest. Each client just takes about 300 lines of code on average. However, without Qi, building an application-specific analysis would require re-implementing all the prerequisite analysis from scratch. Our estimate is that this would take roughly about 20 times more code. In addition, our static analyses are also lightweight, even on a real-world code base with over 1 million lines of code. We're running all of our 40 analyses here, takes about 6 minutes in total, for a 1 million line code base. Okay. There's one last thing I would like to share. Since its release 4 months ago, Qi has also attracted registered users from nearly 50 institutions across the world. And we welcome everyone to visit our website to access full source code of Qi. We also provide extensive documentation to help you get started with Qi and develop a new analysis. In addition, we offer detailed API references. If you have any questions or would like to discuss ideas, feel free to contact us. Thanks for your attention. Oh, sorry. This is our website and open source code, documentation, and API reference. For example, missing.
I think we're
okay.
So you
emphasize case studies. Finding, but not verification. Is the analysis framework sound in general?
For fundamental analysis, we try to keep them as sound as possible for it to be reusable across many clients. For application-specific analysis, considering some practical usage experience, we would do more aggressive optimizations to reduce false positives. Therefore, we may sacrifice some soundness in application-specific analysis, but the fundamental analyses are sound. Yeah.
Well, you said as sound as possible. What does that mean?
Theoretically it's sound, but we cannot ensure there's no bugs in implementation, right? Yeah.
I see. Got it. Thank you.
Thank you for your question.
Very nice talk and impactful work. I have some two questions. The first question is that you find some bugs and how you report this bug to the developers. Do you need to give some kind of input to help them diagnose the issue? And the second problem is that because you listed many different kind of bug types, so what's the expressiveness of this framework? So because, for example, can you handle some bugs that cannot be expressed by the data flow properties? Thank you.
For the first question, we report bugs to developers through GitHub issues or pull request if we happen to find a patch to the bug. This is how we report bugs. And for the second question, not all bugs here are data flow related. For example, for deadlock analysis, it's not a data flow problem, actually.
Okay, thank you for your answer.
Thank you for your question.
Thanks for the talk. This is really cool. Have you seen anybody build any analyses for like questions of physical design, like finding long timing paths or anything like that?
For Verilog static analysis, we have only seen linter-like analyzers. For some backend tasks, such like static analysis or static timing analysis, to find the longest critical path in the circuit design, so they can optimize performance. We have seen some work on that, but that's not from the language level. That's from the netlist physical level. Yeah.
Great. Thank you.
Could I implement sort of static analysis to find timing bugs using what Qi provides?
Actually, you can find critical paths in the source level, but hardware synthesizers do many things during synthesis. So I suppose not, because the physical latency, which is affected by voltage or temperature, those parameters are only available after hardware synthesis. In the source language level, you don't have parameters about physical cell delay. Yeah.
All right. Well, if there's no more questions, I'll thank the speaker one more time.
Yeah, thank you.